Okay, so good afternoon, everyone. I am. We're going to start our live session 4 on this particular topic of technologies for clean and renewable energy production. I am Devarun Banerjee, a PMRF PhD scholar from Indian Institute of Technology, Delhi, and this is our fourth live interaction session of this NPTEL course. So, as you know, in this particular in this particular interaction class, we discuss initially the overview of the lectures which have been provided in this particular week. So in the first lecture in this week, what has been provided as it has been discussed that the various processes for the impurity removal from liquid fuels. So what are the different impurities present in the liquid fuels and their requirement for the removal uh, for their valorization purpose, and different processes how these particular impurities are removed, such as the sulfur compounds, how they are removed, such as by high sweetening process, other elements such as nitrogen, metals, and maybe also other phosphorus and other elements also. This can be also removed via other process such as hydrogenation, hydrotreatment. So in this, I will quickly go to the first lecture. So these are the overview of these different impurities and the requirement of their removal. Uh, and then the different kinds of what are the sulfur compounds and nitrogen compounds which are present in this different petroleum products. Those are discussed. Those are overview, and the different processes for the impurities removal, such as this sweetening process, copper base process, doctor treatment, caustic soda wash, Marox process, which is a catalytic process. So these kind of different processes are also discussed. Mm. In the caustic wash is simply the the thiols are actually reacted with the caustic soda, the sodium hydroxide, and it actually converts as a sodium based compound, so as a NaS, and R is our alkyl group. So the sulfur is removed in this alkyl group and water is covered. And the doctor sweetening process, where the sodium plumbite solution is used, where we treat our particular petroleum product with the sodium plumbite solution and some elemental sulfur, convert the mercaptan to disulfide. So this is our thio oil solution, and with the sodium plumbite solution, it gets converted to a lead based solution, and then further the elemental sulfur is also acted with this, so we get the disulfide kind of things. However, these disadvantages are also discussed, like if too much elemental sulfur is added in this particular step, it will cause a excess formation of polysulfide, which means this kind of disulfide, or this RSXS R, it means that is the multiple the polysulfides. So this is not very much recommended. So there has to be an optimized quantity of this elemental sulfur addition. Another thing is that why I am talking about the optimized quantity of sulfur, which means that a very low quantity of sulfur would also be very much not be very much helpful, because it would lead the mercaptide to be remaining in the oil, and its oxidation to lead the oxide causes failure. So this is the reason that this kind of mercaptide which is formed the PbSr whole twice, so it would then this kind of mercaptide would be remain in the oil, and ultimately what would be happening is that it would go undergo oxidation, and then it would be forming the lead oxide, which is again a very harmful thing. So contrary to that, we need to convert this entire mercaptide to the this kind of sulfides and lead sulfides instead of allowing it to undergo oxidation. Other process is their copper sweetening process, where this particular thiooils are treated with the copper chloride to convert the mercaptans into the disulfur. So this kind of RSSR, which are already discussed. So different forms of is cupric chloride or cupric chloride or can be used, and they would undergo different kinds of processes. Byproducts are there are kind of hydrochloric acid, and again the same thing, that if this kind of the cupras mercaptide, if there is present, which didn't undergo this particular copper sweetening process, then what would happen is they would undergo oxidation and they would form a cupric oxide. So ultimately what is the water tolerance test, it would fail to pass. Other thing is that the catalytic process, such as the Marox process, one of the another successful treating process, which is basically developed by the UOP Honeywell. What are the basically this kind of process is that is the oil phase thio oil and aqueous phase sodium hydroxide, it would get from the NaSr, and similar kind of this aqueous phase NaSr then further undergo oxygen and water, and it would form the oil phase disulfides, which is insoluble in this particular caustic, so it would form a bilayer. So one would be the caustic soda and another one is the disulfides, so very easily separable it would be there. This kind of Merox process, which I already uh, told, is this extraction Merox process. This entire flow sheet has been provided. Some initial caustic pre-wash. As you can see, this kind of caustic pre-wash happens initial, and then there is an extractor, and then whatever extra caustic soda is there, that would get settled. This is filtered, and the treated product we get. And the another system, this regenerated caustic soda, this is what we also get, the regenerated caustic soda, ultimately via this removing the spent air and this separator, this regenerated caustic soda, this again it gets recycled in this extractor, and it get it gets performed in this sweetening process again and again. Okay, here's the further details of this particular Marox reaction. All are these things are all provided, and different examples of the application of the Marox process, that is also provided. And then further, what is discussed also the hydrotreating or hydroprocessing thing, where this direct hydrogenation happens in this particular process to convert the sulfides or the nitrides into other forms. Okay, so among them, this the hydrodesulfurization, where you can see this thio oil can get converted into H2S, and you will just get without any carbon loss. You will just get the with the alkyl group, and there is a extra hydrogen is added. So this and normal sulfides, they are also converted into H2S, and disulfides, they can also get converted without any carbon loss. And then further, this H2S can be processed via combustion, which can ultimately give us CO2 and SO2. And further, uh, this apart from the sulfur, the nitrogen based impurities can also be converted via this hydrogenation, the process of hydrodenitrogenation, that this nitride based process via catalyst and direct hydrogen pressure, they can get converted into D nitrides, where this nitrogen would be gets uh, removed from this structure. Okay. So how this particular nitrogen is gets removed is in the form of ammonia. So in the sulfur, it gets removed in the process of H2S. The nitrogen gets removed via form of ammonia, which is again a very much value-added product used as a fertilizer, and all the other importance are there for ammonia. Apart from this sulfur and nitrogen, metals are also found in this particular petroleum-based products, such as sodium, potassium, lithium, calcium, strontium, copper, vanadium, nickel, chromium. There's lots of metals, and this concentration can be as low as 0.1 ppm to up to even 1200 ppm, right? Uh, so they also can be removed via this different process, such as the de-asphalting process, the thermal process. Among the thermal process, the breeze breaking process, the delayed coking process, the chemical treatment process. Uh, these are all the process which have been discussed in the particular lecture. Okay. So the lecture 2 what had been discussed is as the petroleum residue and its upgradation, uh, which was there in the first lecture. So this further continuation, the petroleum residue and its upgradation, the different routes of this particular residue upgradation, among them which are already told, that the solvent de-asphalting, uh, base breaking, delayed coking, gasification. So lecture 2 and 3 both comprises of this particular uh, portions, the de-asphalting, solvent de-asphalting process, HDA, base breaking, delayed coking, gasification. These are the processes that we discussed in lecture 2 and 3. So 17, yeah. So the different petroleum residue, among them what are they? The atmospheric residue and vacuum residue. So this what happens is that this residual oils differ from the average crude oil in respect of higher viscosity, high sulfur metal asphalting contents, high average boiling point, high condensation carbon ratio, low hydrogen by carbon ratio. So therefore what it means that it doesn't meet the requirement of the commercial petroleum products. So we need a upgradation. Okay. Uh, we are getting a crude oil, and then we are we are passing it through a refinery. So what are there are certain products we are getting different ranges of products with different carbon numbers. Apart from them, there is certain portion of residue present in the via the atmospheric distillation unit. We get the atmospheric residue. It's that particular atmospheric distillation unit product is further passes through a vacuum distillation unit. There we get the vacuum residue. So all these residues, we should not discard it. We need to make it again a valuable thing. We need to make some value added chemicals and fuels from it. So we need to upgrade it. Among them, what is there? There's the residue oil. The residual oil can be described as a colloidal system in which the dispersed phase is composed of asphaltenes and resins. So this is a kind of a oil where is a colloidal system, not an exactly a solution, but a colloid. So what happens is that this kind of residual oil having a high viscosity, high heavy metal content, high salt content, sulfur nitrogen content, naphthenic acid content. Okay, and this kind of a micelles are actually formed in this kind of oil, where there are the two kind of sets, the hydrophobic and hydrophilic end. Okay, and therefore this particular residual oil needs to undergo different kinds of upgradation. What are these upgradation processes? Among them, there is extraction based upgradation process, which is solvent deasphalting process, thermal conversion based process. What are the thermal conversion based process? It means cracking and gasification. Among cracking, you will all get further processes such as vis breaking, delayed coking, fluid coking, flexi coking, hydro vis breaking, donor solvent cracking, hydropyrolysis. Okay, and other thing is that what is this catalytic process, which is the hydrogen pressure based process, hydro processing or hydro treatment. Among them, what are there is a hydro cracking. So in the presence of hydrogen, you have to crack, or you have to cleave the particular carbon carbon bond, or whatever different other types of bonds. Okay, and this kind of process can be catalytic, as I said, or it may be non-catalytic. So in the non-catalytic process, what would be there? The pressure, temperature, time requirement to be more. So you have to optimize the process. So overall, this is an overview of this particular different upgradation techniques, such as the hydrogen addition. So hydro desulfurization, I already discussed the carbon rejection process. Among them, what kind of systems are used? The fixed bed system, the ebullited bed system, the slurry bed system. Okay. The carbon rejection system is there. Carbon rejection means there is a cracking. So the it can be a catalytic process. It can be only based on a high temperature and pressure. So thermal cracking, catalytic cracking. There are basically two. Apart from them, what is there? The solvent deasphaltation, solvent deasphalting process. Okay. Apart from that, again, what is there? To give a very high temperature. Okay, and in the presence of air or steam. So what would be there? The whatever carbon based products are there, they would be vaporized. They would be transformed into some high vapor pressure system. Okay, so in this is the basically gasification system. So ultimately you can try to get syngas like product from it. Okay, is this worldwide distribution of commercial residual capacity. The solvent deasphaltation process is also discussed in this particular thing. The vacuum residue is provided in the solvent deasphaltation, which undergo the further processing to get the bitumen CFDC gasification process, and we get the power generation there, the steam generation there, hydrogen, petrochemicals, different fuels like that. And further solvent deasphalting overall refinery process is also shown. Different kinds of solvents are used in this, like propane, butane, pentane. There are different types of solvents, like lighter solvents, high, propane, isobutane, or heavier solvent, butane, n-butane, n-pentane, or isopentane, and even light naphtha are also used. Okay? The process variables, which are the process variable parameters, are the solvent composition, solvent to feed ratio, temperature, the pressure. These are all the solvent parameters. Okay, and again, when we're using a large excess of solvent, we need to recover that solvent in a commercial process. Okay, so how this particular solvent recovery can take place? It can take place via evaporative mode, supercritical mode. Okay, so this can be a single effect evaporation, there can be multiple effect evaporation up to 3 stages, and this supercritical mode in the you get the touch the critical point of the solvent, and you go beyond that, which is the supercritical phase or supercritical zone of this particular solvent. Okay, and in this solvent, what can be happen, that it from 85 to 93% solvent can be recovered as a lighter phase for heat exchange and recycle in the process. Okay, further detail of the de-asphalting towers, how it can be actually designed. The internals, the column internals, what does it mean by the column internal? It means that the rotating disc in contractor, the packing, how the packing would be made, how the baffle trays can be positioned to minimize the losses and maximize the heat transfer and mass transfer coefficient. Okay? And further processes apart from the solvent deasphalting process, as the vis breaking process, the delayed coking process, the gasification process. Vis breaking, which means that the viscosity breaking, so lowering the viscosity. which is a mild process, predominantly a liquid phase thermal cracking process in easy words. Okay, what is happening in this is the high molecular weight hydrocarbons, they are basically broken into lighter versions of it. So into the lower molecular weight hydrocarbons, they are converted. Okay, and ultimately what happens is that with this particular lowering of the carbon numbers, the viscosity is also lowered and the pour point is also lowered. Okay, so the petroleum residue, these are actually converted into small amounts of light hydrocarbons such as LPG, such as naphtha, gasoline, heavy gas oil. Residual part is reduced viscosity. Okay, this kind of different uh, light hydrocarbons which are made. And this particular base breaking mechanism is based on initiation reaction, chain propagation reaction, and further chain termination reaction. So it happens via free radical mechanism, where it gets activated by formation of a free radical. Then this free radical further activates of some pristine molecules like this C6 molecule. It generates further free radicals of C6 hydrocarbon. Then this kind of different free radicals, uh, what happens is when two different free radicals are joined, or these two types of free radicals combine, this kind of chain reaction gets stopped. Until till then it just uh, continues. Okay, further this overall base breaking process, what it shows is that the initial preheater. After that, there is a furnace, there is a soaker drum, the fractionator column, and this. Further, if we want to upgrade the residue tar also, we can provide another vacuum fractionator. Okay. Apart from the vis breaking process, there's a delayed cooking process where we take a much more time for the formation of coke, which is actually coke is actually one of the disadvantageous thing for a particular hydrocarbon based process, uh, which deactivates whatever catalyst you are using. It blocks whatever reactor we are using. So need to delay this particular coking thing. Okay, and its mechanism is also in this particular thing. Two types of different reactions take place in this particular reaction. The primary reaction, what happens in the primary reaction, the decomposition of large molecules into small molecules takes place. In the secondary reaction, what happens, the active products from primary cracking reactions, uh, so first the primary reaction happens, there is small molecules generated from the large molecule. These small molecules further get cracked, cleaved, or react to form some other compounds, or may get combined, polymerized to give further heavy products. Okay? These kind of different mechanisms are also provided. Have to read them thoroughly, and different kinds of whatever the products we get, the gas, the liquid, the solid, this kind of different products we get. And further, the what are the operating variables in this particular delayed cooking process are the transfer coke drum temperature, the pressure, the recycle ratio, the reaction time, how much steam is added in this particular process, the coke yield. Ultimately what will be happening is that these particular process variables would what would say that uh, they would be applied to vary the different parameters or different output variables. What are these particular output variables? They are the coke yield, such as the coke yield would be decreased as the coke drum temperature increases. Okay, and now it is also important that the now it will say that okay, they will keep the coke down temperature as low as possible. That would also not be very much helpful. If the temperature is very low, the cooking reaction would not proceed, and ultimately what would be happening, some soft type of coke would be formed instead of this carbon upgradation should be happening, and this kind of a very unstable type of soft type of coke would be formed. Okay, so similar thing, a very high temperature is also not very beneficial. The very high temperature also makes the coke removal difficult from the drum. Okay, so again this optimization is very important there, because the temperature, what it does is that it controls the volatile combustible matter of the coke products. So the variability in this particular different volatile matter, the combustible matter of this particular coke products, uh, is actually can be controlled by varying the operating temperature. Okay, similar thing is the coke drum pressure is also important. So if you decrease the coke drum pressure, what would be happening is you get a benefit of the reduced coke yield. Okay, but again you have to optimize it. A very low coke drum pressure would also not be beneficial from the product point of view. There are these kind of different formulas for coke yield, for naphtha yield, the gas oil yield, and other gaseous products from C4 onwards. The yields of them, they can be actually calculated from the CCR with percentage value. Okay? These are the different examples of this, what kind of technologies are used, what kind of feedstock are used, where this particular plant is located, and the seamless cleaning option is what is there, and what are the products we are getting from this particular system. These are overviewed. Okay, and the fourth lecture, what it contains is that the heavy crude oil and its properties. Okay. Mm. The problem in heavy crude oil. So what are the basically the challenges in the heavy crude oil we face, and basically it's a solution in a modern way, in a modern refinery. So how it can be solved, and in the conventional refinery flow sheets, the requirement of wellhead processing, the different technologies available for wellhead processing, and the different advanced refinery configuration for processing heavy crude oil. These are all discussed. Okay, so this particular lecture is all about the heavy crude oil processing. uh, so it contains a different ranges of uh, products, such as the light oil, medium heavy oil, extracellular bitumen. Okay, and the what is the problem in this particular heavy crude oil and thing is highly viscous. Therefore what happens is that the pipeline transport is very difficult, and automatically what happens is that the conventional refinery, it cannot actually accommodate kind of highly viscous, high acid number, high sulfur content heavy crude oil. Okay, therefore we need to make it undergo some process. Okay, so that it gets fit into the conventional refinery. So this heavy crude oil processing is important. Therefore, so what are the basically operational requirements, or operational changes are required in this particular heavy crude oil processing? That we require basically a higher heater temperature. So automatically when you are having a more impure, more viscous oil, so it will be automatically get processed or decomposed at a higher temperature. uh, Lower operating pressure in the both atmospheric column and the vacuum column. Okay, lower atmospheric column, the improved wash section efficiency, and a better ATVTV stripping. Okay, so if you need to maintain a certain quality of this particular product which we are getting, we need to uh, maintain all this process. Okay, and further different conventional refinery flow sheets are discussed in this particular process. uh, the conventional technology summary is provided. What is that? The heavy crude is transported to refinery from the production field. So for this particular high viscosity, what it requires is that it requires a high pumping cost. So the desalting is not very much easy. Okay, and further, the fractional distillation produces different liquid products, gas and residues. Okay, so and it is a basic overview of this particular conventional refinery technologies and the primary conventional conversion processes. What are there? This cracking process, the hydroprocessing, the solvent deasphalting process, the delayed coking, the vis breaking. These are the primary processes. Okay, secondary processes, what is there? Is hydroprocessing. Okay, these are all discussed again. Uh, so these are the different difficulties in the conventional refinery process and a wellhead processing we need to undergo. So different wellhead processing, what are there? There is a heavy oil upgradation technology, there is improved delayed coking unit, the shell upgrader technology, the GHU upgrading technology. What is the GHU? This is the gen oil hydroconversion upgrader and the solvent extraction named as ROSE. So these are the different examples of these different advanced technologies which are actually nowadays getting promoted. Okay, so this was the advanced refinery configuration for the processing of the heavy crude oil. It's the overall schematic. Okay, then we'll discuss some of the question answers after 2 minutes. Okay, the first sample question is that the crude oil distillate impurities may be removed by chemical reagents is the one option. Okay, apart from that, and what is the other option? By catalyst, by adsorption on clays, by caustic sweetening. All of these are correct. The correct answer is that all of this, as I've already discussed, that the processes for impurities removal, it involves the caustic wash, doctor treatment, the Marox process, which is a catalytic process. Caustic wash means is the sweetening process, apart from that the copper sweetening process. So these are the different processes and for the crude oil distillate impurity removal. Okay, so all of these will be the correct answer. Next question is that is an example of a reaction. The C2H5 dot means it's a free radical. So C2H5 free radical plus C6H14 would give A plus B. What would be the A and B? Is it a C2 molecule, C3 molecule, C1 molecule, or C8 molecule? A, and automatically the rest of the carbon would be going to the B part. So C6, C5, C7 without any carbon. So the correct answer is that yeah. So the correct answer is A. Yeah, automatically it is basically an example of the vis breaking mechanism. So as I told earlier also, it happens via a free radical way, where the initiation step, then example is that C6H14 gets broken into two types of free radical, and then these free radicals further breaks this particular C6H14 kind of thing. So one of it breaks in a C2 and C4 type. Okay, so one of this C2 type free radical, it reacts with this C6 hydrocarbon, and it generates uh, one of the C2H6 and C6H13. Okay, so this is A is the correct answer. And further, the other types of free radical is a 4 carbon free radical. It also reacts with this C6 H14 molecule, and also the uh, formation of the free radical would be same. So this you have to remember. Okay, this C6H13 free radical would be formed. So the rest number of carbons would be given to the other portion. Okay, and then further this when these free radicals would be combined, this chain would be terminated. This will be the termination portion. The next question is that to reduce the furnace temperature, a soaker unit is placed between the flash chamber and furnace. What is the operating temperature and pressure for soaker unit? Is it 440 to 460 degrees Celsius and 5 to 15 bar, 400 to 430 degrees Celsius and 15 to 20 bar, 480 to 5000 degrees Celsius, 3 to 5 bar, 320 to 420 degrees Celsius and 15 to 25 bar? Yeah, right. So the correct answer is the 440 to 460 degrees Celsius, 5 to 15 bar. Okay. So this is again an example of the vis breaking uh, thing, where there is the after the preheater there is a furnace, and there is an optional cooker drum is actually provided before the fractionation column. Okay, so the correct answer would be 440 to 460 degrees Celsius between 5 to 15 bar. Okay, and so the next question is that these are different types of example of the cokes have been provided to tell that what are the form of these cokes. So the different A, B, C, these are three types of cokes are there. What would be the correct answer? Yeah, the correct answer is the sponge coke, short coke, and the needle coke. So these are the basically the products of the delayed cooking. Okay, these are the basically solid products. So the different kinds of variation of the operating parameters would give us the different kinds of cokes. Okay, so different kinds of what by mean that the different kinds of coke, it mean that the sponge coke, the short coke, and the needle coke. Okay, the different types of coke have these kind of different types of applications. Okay, one of one other one two kinds of application you would have read already in this particular lecture also, and some question is also there. Okay, regarding this application. So as we're talking about this particular application, I have to tell what kind of coke is used in the production of high grade graphite electrodes for the application of electric arc steel industry. Sponge coke, short coke, needle coke, or all of them are used. Yeah. So the correct answer is that the needle coke. So needle coke is kind of a premium quality coke which is used in the production of high grade graphite electrodes for the application in the steel industry. Okay, specifically electric arc steel industry. So uh, what happens is that these kind of needle coke properties would be depending on the, as I already told, as the operating temperature, operating pressure, residence time. These kind of operating parameters would be very important, and obviously your reactor, coke drum specification, the design, how you're designing your coke drum, how you're designing your fractionating column. Okay, so this kind of things would be very much important, and how what is the your feed quality automatically. So the carbon quality, the calorific value quality, what is there in the feed should be also important. So you have to identify the ABC in this particular image. Okay, this is the delayed cooking process flow sheet. Uh, some options are the heater, fractionator, gas oil stripper, fractionator, gas oil stripper, heater, gas oil stripper, fractionator, heater. So these are the have to arrange them. So what is the A, what is B, and what is C? This is a delayed cooking process flow sheet. There is initially this is the coke drum, and then this particular steam injection is there, and then it goes from this particular unit, and ultimately this particular unit. So the correct answer is the heater, fractionator, and gas oil stripper. Okay. So initial thing is that you have to heat it, preheating, and then the heated form would be going into the fractionating column. Okay. And from the fractionating column, you have to separate them via stripping section. So our gas oil stripper would be there, and in the downstream. Okay. So the gas oil stripper, it would be providing us the gas oil as the output product. Okay. So the gasoline percentage can be calculated by what is the correct formula? Gasoline weight percentage equals to 111.29 plus 0.343 into weight percentage CCR is 112.9 plus 0.434, 11.29 plus 0.343, 2.89 plus 0.434. What is the correct answer regarding the relation between the gasoline weight percent and the CCR weight percent? So the correct answer is the gasoline weight percent is equals to 11.29 plus 0.343 multiplied by weight percentage of CCR. Okay, it has been also shown in the coke yields formula in the particular slides in this week lectures. That is the shown here. Apart from them, there are other formulas such as coke yield weight percentage, gas weight percentage, gas oil weight percentage, gasoline volume percentage, and gas oil volume percent. For this volume percentage normally you need to know the degree API and the weight percentage of gasoline. For that you need to use this kind of formula, and for that you need to need the weight percentage of CCR. Okay. So the next question is the vacuum residue have contraction carbon ratio is a CCR percentage as I told just earlier. As a 20 weight percent, the degree API is 8.5 degree API. The sulfur content is 3 weight percentage. Now it is also fed into the delayed coker unit at a rate of 4 lakh pound per hour. So you have to determine the production of the naphtha in the percentage. So the correct answer is the 18.15. So the naphtha weight percentage, the formula is similar as the gasoline one. Naphtha weight percentage equals to 11.29 plus 0.343 into weight percentage CCR. So you have to just put the 20 here. So 11.29 plus 0.343 into 20 equals to the 18.15 percentage. Okay. The same values you have to also determine in this particular thing the percentage of the coke. Okay, the coke weight percentage. Given the CCR as 28%, API is 8.5 degree API, sulfur content as 3 weight percentage, and the rate of the feed is the 4 lakh pound per hour. So the correct answer is the 32. As we have seen earlier also, the coke yield weight percent is have a direct relationship with the weight percent CCR is 1.6 multiplied by weight percentage CCR. So it just puts the value 20, 1% 20 is a 32%. Very simple thing. Now the next problem, what it says that a gas oil with a degree API gravity of 40 and a sulfur content of 1.58% is fed into a hydrotreater. At this particular thing is another thing I have mentioned is 1 barrel equals to 306 pounds. Okay, so it is required to carry out the hydro desulfurization at a 80% severity. So you have to determine the hydrogen required. So there is a correlation which is there uh, for the hydrogen requirement is 110.8 into the weight percentage of sulfur in feed, which would be the 110.8 multiplied by 1.5 plus 10.2 into hydro desulfurization severity, which is 80. So plus 10.2 into 80 minus 659. This would be your uh, whatever the hydrogen required per unit barrel. Okay, per unit barrel. So by chance, whether it says that you have to determine with per unit pound, you have to just again divide it by 306. Okay, but this formula is for per unit barrel. You have to remember that. So this SF is the weight percentage of sulfur is 1.5. You have to put 110.8 into 1.5 plus 10.2 into 80 minus 659. Very as simple as that. We have already discussed this particular thing. What is the name of the process? It's a delayed cooking process, bees breaking process, fractionation of crude oil, catalytic cracking. What is the name of this particular process? Yeah, it's already discussed. It's a delayed cooking process. Okay. The next question is that the sweetening is the process for removal of what kind of compounds from petroleum products? Nitrogen, sulfur, aromatics, and high molecular weight alkenes. Yeah. The correct answer is the sulfur. So there's a apart from the nitrogen metals, there is a sulfur which is present in the major quantity. So the crude oil, crude distillation, cracking, and other refinery processes, it contains this kind of impurities, which actually have the sulfur, nitrogen, oxygen, dissolved metals, inorganic salts, and soluble salts dissolved in emulsified water. Okay, so these kinds of impurities needs to be removed to achieve the quality of the finished products, color, odor, oxygen stability, etc. Okay, and then also to prepare to use it as feedstock for other processes such as polymerization and reforming, in which catalysts would be harmed by impurities. So we this kind of thing among them. The initial thing also, there was one question also, that the impurities may be removed by what are the processes. So you see that all the processes are mentioned: chemical reagents, by catalysis, by adsorption of clays, or by similar materials. And among them, specifically the sulfur compounds can be removed by sweetening process. Okay, as I told earlier, the sulfur is the most important thing for the refinery process. And the caustic sweetening or the copper based doctor treatment or the hydro treatment, these are the various processes for this sulfur removal. So the next question is that these are different sweetening processes are there. Okay, the caustic sweetening, copper sweetening, daughter treatment. Okay, so what is the correct reagent with them? The options are the sodium plumbite solution, sodium hydroxide, copper chloride, copper sulfate. Yeah, is it correct? I have told is P2, Q1, R3. Okay, so I've already discussed the caustic was is happening by the caustic soda, sodium hydroxide, sodium plumbite is used in the doctor treatment. Okay, and the copper sweetening, the copper salt which is used is the copper chloride, not the copper sulfate. So remember. Okay, the genoil GHU upgrading process is based on what kind of reactor? Fluidized bed reactor, moving bed reactor, fixed bed reactor, or none of the above? Okay, so the correct answer is the fixed bed reactor. So the genoil GHU upgrading process is basically a flexible hydroconversion process. Okay, so the hydrogenation, and by the virtue of the hydrogenation, the conversion of our oil, okay, this heavy crude oil, this conversion happens in the one stage, and it can be applicable for a wide range of things, wide range of feedstocks such as sour, acetic, heavy crude, heavy refinery feedstock. And it is stable at a high conversion level. Flexibility, this kind of flexibility and wide variability is important, and it's actually very economical for 10,000 gallon per day capacity. uh, and a bit of technical things as there is a is happens via a fixed bed reactor system with a reactor sequence and the catalyst distribution to protect the more active hydroprocessing catalyst. Okay. So there is basically two types of reactors there. There's a two types of catalysts are also present, but the hydro demineralization kind of catalyst is there in the first reactor. The metals and all the minerals are removed. The second reactor, hydro desulfurization, hydro denitration, this kind of sulfur nitrogen removal is there. The second reactor. Ultimately, the what had been unconverted is sent to the syngas unit for the hydrogen recovery. Okay, and the leftover gases it is filled into the steam turbine based system with the IGCC. Okay, integrated uh, capture and conversion process. We cannot just the carbon based gases we cannot let into the environment. We have to somehow process it. So we need to generate some power and steam out of it, and then therefore it is processed in the IGCC system. Next question is that which of the following is the secondary conversion operation of the crude oil processing? Cracking, grease breaking, coking, and hydroprocessing. Remember, this is not a more than one option correct thing. This is only one option would be correct. What is the correct one? Hydroprocessing, coking, grease breaking, or cracking? Yeah. So the hydroprocessing is the correct one. Is the secondary conversion operation of the crude oil processing. Okay. So initially the primary processes are these breaking, delayed cooking, and the whatever product we are getting from it, then we use it in this particular system. So the soaker grease breaking process is carried out at what kind of operating conditions? High temperature, high residence time, low temperature, low residence time, high temperature, low residence time, or low temperature, high residence. Yeah. So the correct answer is the option D. You are right. Is a low temperature and high residence time. So in this particular grease breaking process, what happens is that the temperature is about 440 to 460 degrees Celsius with the 5 to 15 bar with about 20 to 30 minutes of residence time. Okay, this is the in the grease breaking process. Okay, so the soaker grease breaking process is a relatively low temperature. Okay, and the very high residence time. So the different types of grease breaker is there. The coil grease breaker, if you see the competitive thing, is a 100 to 300 second for coil grease breaker, whereas you have to give a 1200 to 1800 seconds for the soaker grease breaker. There is a high residence time thing with a comparatively low temperature. Or on the contrary, if you give a high temperature, you will be requiring a low residence time. You have to balance that. So another numerical thing is that the gas oil of 1 dBl with a degree API of 50 and a sulfur content of 2.58% is fed into a hydrotreater. It is required to carry out a hydrodesulfurization at a 82% severity. Calculate the hydrogen required and the degree API of the product. These are the correlations given. What is the correct answer? So the correct answer will be the 454 SCF per BBL and 51.3 of the degree API of product. How it is coming? It is simple. This is a formula given is 110.8 into the multiplied by the sulfur content of the feed, which is 2.5 plus 10.2 into the hydrodesulfurizing HDS severity, which is the 82 plus 10.2 into 82 minus 659. Just calculate it, you will be getting 454.4. Okay, and the what is the degree API change from feed to product? We have to identify that first. Okay, this is a delta thing is there. So, however, what is been asked is the degree API of the product. So, for the delta is the formula given. So, delta means the change. So, 0.00297 into the hydrogen field. I have already determined 454.4 minus 0.11205 into API of feed. API feed is 50 plus 5.5419, which comes around 1.3. Okay, so this is the delta change. So already we had a 50, 50 plus 1.3, 51.3. So 51.3 will be the degree API of the product. So this B is the correct answer. So you have to match the typical property of crude oil with the difficulties in conventional refining approach. Very high viscosity, high metals, high carbon. What would be the correct option there? Need expensive hydrogen, refining problems, shipping problems. What is the disadvantage we face due to whatever reason? To match them. Yeah, so you're right. It's P3 Q2 R1. P3 means very high viscosity. What would be happening? A shipping problem will be there. So you need to transport a very thick, slurry kind of thing instead of a very low viscous thing. So there will be a transportation problem. So high viscosity would be correlated with the shipping problem. The high metals is the correlated with the refining problems. So we will be having a greater ppm level, even more than maybe even ppm level of metal in the feedstock in the crude oil. So there will be a problematic thing for the refinery operations, right, to process them. Okay, and if you have a high carbon, which means that for breakage of this particular carbon to undergo the cracking, to process, to undergo gasification, and all these processes, you need a more and more pressure of hydrogen, which ultimately becomes a which is termed as a high expensive hydrogen. Okay, so this is the correct one, the P3, Q2, and R1, and these are the overall problems we have discussed, and the conventional refinery approach problems are discussed. Okay, that is all from my side today. If you have any query, you can ask. Otherwise, we'll discuss. Okay, it seems there is no queries, so we'll stop here and see you next day. Thank you.